In this video, we're going to introduce a topic known as electronegativity. Now, really the starting point for this conversation is to focus in on what we call polar covalent bonds, right? So polar covalent bonds. And an example of a polar covalent bond is hydrofluoric acid, HF. And what do we mean by polar covalent bonds? So we kind of talked about this a while ago, but just as a refresher, let's think about what would happen if we had a container of hydrofluoric acid or of HF gas, right? If you had just a container of HF, then you would have these molecules in some sort of random orientation, right? So they would be in the container, and you would have some oriented one way, some oriented another way. It would really be more or less a random kind of distribution of orientations, possible orientations for HF in this container. Now, if you were to apply an electric field to HF in this random orientation, what you would notice is that the fluorine would be pointing towards the positive end and the hydrogen would be pointing towards the negative end of your applied electric field. So basically orienting themselves in a very ordered fashion. So you would go from this random orientation to an ordered orientation that depends on the relative pole that the molecule is at, right? So the fluorine would face towards the positive pole and the hydrogen would face towards the negative pole. So what this is indicative of is an unequal sharing of electrons. And that's what a polar covalent bond is. It's a covalent bond where there's an unequal sharing of electrons. Right? So because we have this unequal sharing of electrons, the fluorine is going to be slightly negative and the hydrogen is going to be slightly positive, right? So if we're looking at HF is going to have a partial negative charge, which we use the small Greek letter delta to denote a small charge. So it's partial negative charge on the fluorine and a partial positive charge on the hydrogen. Because of this disparity in charge, that's why the hydrogen would point towards the negative end of the pole, and fluorine would orient itself towards the positive end of the pole. Because of this charge disparity, any applied electric field would result in an ordered orientation for this molecule, because there's going to be an unequal sharing of charge here. So now, how do we quantify this unequal sharing of charge is the question, right? So that's where electronegativity comes into play. So electronegativity is a way to quantify an atom's ability to attract a shared electron pair, right? So this is the ability of an atom to attract an electron pair. Now, this is related to the ionization energy, but it is actually a different concept. So the ionization energy is the ability for a single atom to gain a single electron. The electronegativity is going to be the ability for that atom to attract an electron pair when it's involved in a covalent bond. So related properties, but not exactly the same thing. All right, so how do we actually quantify this? How do we actually put a number to this concept of electronegativity? Well, we use something known as the Pauling Electronegativity Model. So this is the Pauling Electronegativity Model. And so this was a model developed by Linus Pauling, who won a Nobel Prize in chemistry for all of his early work in chemical bonding. And he came up with an electronegativity model, a way to actually quantify this electronegativity for a given atom. So what he did was use a baseline expected bond energy for a given atom with hydrogen, right? So what he would do is take an expected bond energy. So let's say we have hydrogen bonded with some atom X, right? So just any atom X. So there's going to be an expected HX bond energy. And that's going to be equal to the bond energy of a hydrogen-hydrogen bond. So the hydrogen-hydrogen bond energy plus the XX bond energy right? And then we're going to divide that by 2, right? So what this is basically saying is that what you would expect the HX bond energy to be would be a hydrogen-hydrogen bond energy plus the XX bond energy. So if X was bonded to X, that bond energy, hydrogen bonded to hydrogen, that bond energy, and divided it by 2. So what are we assuming here? So in this expected bond energy, you're assuming that the electrons are shared equally, right? So this equation, since you're just dividing by 2, it assumes that the bond energy contributions from each atom are equal, which would mean that they're sharing the electron pair equally. And then so what Linus Pauling would do in his model is measure the real bond energy of HX, compare it to this expected bond energy, and then take the difference to get an electronegativity value. So he would use the Greek letter capital delta to denote his electronegativity values. And so he would take the HX bond energy from an experiment, so we'll call this the actual HX bond energy, minus the expected HX bond energy, right? And get a number based on that, right? So this is going to be this delta is your Pauling electronegativity value. So hopefully this makes sense, right? You take an actual measurement of the HX bond energy, you compare it to what you would expect if you assume that the electrons are shared equally, and that difference is how much that atom is attracting the electron pair to it, based on, this comparison with expecting that the bond energy has equal contributions from both atoms, right? So then that gives us a scale. And on this slide, I have all of the Pauling electronegativity values for everything in the periodic table except the noble gases. And so what you'll notice is that this actually follows a very similar trend to the ionization energy, right? So I said these were related, not exactly the same, but they're related, right? So you see that the electronegativity increases as we go to the right of the periodic table and increases as we go up the periodic table, such that fluorine is actually the most electronegative atom on the periodic table, right? So, so basically with this electronegativity value, right? So let's say if we have the delta equal to 0, right? Let's say delta is equal to 0. Let's go back to the equation, look at what that would mean, right? If delta is equal to 0, that means your actual and expected are the same, right? So that would mean that you're looking at a pure covalent bond, right? So if delta is 0, then this is a pure covalent bond. Both atoms must be exactly the same. They must be sharing that electron pair exactly equally. However, if delta is not equal to 0, right? If delta is not equal to 0, then that means that you have a polar covalent bond. Right? And so you can see that with this electronegativity value, again, kind of going back to looking at different types of bonds, right? An ionic bond would be formed between two atoms that have very different electronegativity values. If we look at sodium and chlorine, right? Chlorine has an electronegativity value of 3.1, and sodium has an electronegativity value of 0.93. Very different electronegativity values. Sodium is just going to give up that electron, right? They're not even going to share it, right? So basically, this electronegativity model gives us a way to quantify electronegativity and be able to put some meat on the bones as far as this idea of sharing electrons in atoms, right? So we can actually quantify how much particular atom is going to attract an electron pair to it.